Welcome friends. Let's start from 71 number question. Okay. So it is given that in inelastic scattering, phonon's wave vector kp, or we can say k phonon, is related to incident wave vector k in and scattered wave vector ksc, that means scattered wave vector, and where this is capital G vector is the reciprocal lattice vector. Okay. So basically we have to find the relation between this KSC, okay, with the K in the reciprocal lattice vector and the K phonon. Okay, so let's find. Actually, before going to solve this question, you should know that there are two kinds of scattering process that may happen inside the crystal. Okay, what kind of crystal? What kind of scattering process are there? There are two kinds of scattering process. Okay, so one is elastic scattering, that is normally known as normal process or N process, and the second one is the inelastic scattering, or we generally it is called as U process. Okay, and this particular question is coming from the inelastic scattering. Okay, as it is mentioned explicitly. Okay, it is inelastic scattering. So you see, when any photon, this is a photon, the incident any lattice point, okay, this, or we can say reciprocal lattice point, because we are dealing with the inverse space, that means momentum space, so it is a reciprocal lattice space. Okay, any photon coming in this direction, scattered from this lattice point, or we can say reciprocal lattice point, and it is scattered in this direction k dash. Okay, so what happens in this case? Apply the vector addition formula, as you know from the 12th class, vector addition, head to tail. Okay, and you will get k plus g equal to k dash. That means k incident equal to k incident plus reciprocal lattice vector g is equal to k dash. That means the wave vector for what? The wave vector for scattered photon. Okay, this is the situation. And if you apply the momentum conservation, then it will be s cot k plus s cot g is equal to s cot k dash. Okay, now if you apply conservation of momentum, then you will get s cot omega is equal to s cot omega dash, where this omega and omega dash are the frequency of incoming photon and the scattered photon respectively. Okay, as I have written here. So actually, after applying the conservation law, we are getting that there is no change in phonon. There is no change in frequency of the incoming photon. That means the phonon which is coming or scattered from the reciprocal lattice point, it is not giving any energy to the lattice. So if any photon coming and hitting and scattered back, but it is not giving any energy, that means there is no chance of lattice vibration. Lattice vibration can only happen only when the incoming photon transfers its energy in quantum. Okay, in quantized form, if the scattered photon transfers some of its energy to the lattice, then there is a creation of a phonon, and that creation of phonon will leads to the lattice vibration. But as it is not giving any energy to the lattice, so there is no possibility of lattice vibration. Okay, because there is no creation of a phonon, because lattice vibration, the quanta of a lattice vibration is the phonon. Okay, so as there is no creation of phonon, especially in elastic scattering. Okay, so if you go to inelastic scattering, in this case, if you see, there is a incoming photon and it is scattered with some k dash, and in this process a phonon is created here. You see, this downward coming arrow means a phonon is created in this process, whose whose frequency is WQ. Okay, you see, and the wave vector is Q vector. Okay, so now you apply the formula of wave vector conservation, then you will get this. Remember, here is a positive sign here. Okay, because why I am mentioning this positive sign here? Because this is for only for creation case, when phonon is created. But when there is another case when phonon is observed in this process. You see, in this process a phonon is observed, In this case, if you apply the uh, conservation of that wave vector, then you will get negative sign here. Okay, and if you apply the conservation of energy, see, then you will get there is a mismatch of incoming frequency of the photon and the scattered photon. Okay, that means what? That means the incoming photon which is scattered from any lattice point is giving some energy to the lattice. That means there is a possibility of creation or absorption of a phonon. That's why the lattice is can be in the vibrational state. Okay, so that's why this negative sign and positive sign are denoted here for absorption and creation. Okay, so if you combine these two equations, this is equation 2 and this is equation 3. If you combine this and write it in a compact way, then you will get a negative positive sign both in this equation. And if you rearrange this, that means you will, if you throw back this k dash to the left side, and you will get ultimately you will get this equation. That means the k scattered is equal to k incident plus this reciprocal lattice vector and plus minus k phonon. Okay, so option B is the correct one. Okay, now coming to 72 number question, it is given that in Debye model at a low temperature the specific heat Cv is related to temperature as what power of T. Okay, Cv is proportional to what power of T. Okay, in low temperature case in Debye model. Okay, Debye model is the last model. Okay, in after that Einstein model. Okay, now if you see the solution, how can you find? The main process is you need to find that go back to the last, this we need this, that means we need u first, then if you differentiate this u with respect to temperature, because this internal energy u is a function of temperature. Okay, so if you get this value of u and differentiate it with respect to temperature, then you will get the relationship with the temperature with the, that Cv. Okay, but before that you have to find u, internal energy. Internal energy is the total energy which are depending temperature in the system. Okay, so and this mean internal energy is the average, you can say average internal energy of the system. Okay, so if you differentiate this or integrate it, this du from 0 to nu d is the Debye frequency. Okay, and the g nu du nu into this mean internal energy, where this g nu du nu is known as the number of a frequency mode in the range nu to nu plus d nu. Okay, actually we need to find the number of states, then we can multiply this internal mean internal energy with that number of modes, then you will get the total internal energy of the system. Okay, now if you see in the second step, I have split this equation in two terms. Here in the subscript I have written L means longitudinal, and here I have in the subscript I have written T means transverse mode. Okay, this is longitudinal mode and transverse mode. That means the number of modes coming or contributing in this case has two kinds of modes, or one is coming from longitudinal and T is coming from transverse. Now you see, for longitudinal the contribution of a mode is 1, because the atom can move in rightward direction or in the leftward direction, you can say. So there is only one kind of a mode in longitudinal case, and in transverse case there are two kinds of modes, like this wave. Okay, let's suppose this is vibrating along y-axis. Okay, and there is let's suppose this is vibrating along y-axis, but at the same time it is moving in z direction, let's suppose. That means it is transferring energy in the z direction. Then there is a possibility of a vibration of along x direction. Okay, this is vibrating along x direction. This wave can vibrate along x direction and y direction respectively, but in both cases the transfer of energy is along z direction. Hope you are getting my argument. Okay, That means there are two possibilities, or you can say this is the polarization, two state of polarization of an electromagnetic wave. Okay, so that's why I have written 2 here, and for longitudinal I have written 1 here, because longitudinal contribution is 1 and transverse contribution is 2. And this VL and VT are the velocity in longitudinal case and transverse case. And I I I think you are getting my uh, what I am trying to understand you. Okay, and in this case I am ignoring or neglecting so much steps behind this, because this is a hectic process to solve all of this process. Okay, so I am neglecting, and I have directly written uh, the equation in the last. Okay, so now in this equation, here you can see this theta d. Theta d means the dy temperature here. This theta d means dy temperature. Okay, now if you impose the constraint that is at low temperature, very low temperature, that means t smaller than, very smaller than theta d. Okay, if this happens, then theta d by t will be very high, or you can say it tends to infinity. Okay, so now if you put this constant in this equation, okay, you will get 9 by 8 r theta d plus, you have to solve this integration now. Okay, and if you, after solving, you will get for this particular encircled uh, integration, you will get pi to the power 4 by 15, and this is a constant term. Okay, if you multiply this, you will get this. Okay, now what you have to do, you have to differentiate this with respect to temperature. Okay, then you will get, after integration, you will get this. There is nothing worry to calculation of this constant term, because in the question we have to find only the dependency. Okay, this is the dependency, ignore this constant part. Okay, so the graph is like this, up to this, up to this is increasing like t to the power 3, because it is low temperature. You see, it's a temperature, it's a low temperature. In the low temperature range, this is increasing as a t to the power 3. After some range, it will be constant like 3r, as like as we have got in case of Einstein model. Okay, okay, so now coming to the question number 73. In the 73 number question, it has given that E1 is the energy of the lowest state of a one-dimensional potential box of a length a and particle of a mass capital M. E2 is the energy lowest state of energy when length of the box is half and mass of the this mass is doubled. That means 2 capital M. Okay, and you remember, you see that in this problem, it is mentioned that there is no mention of what kind of a potential box this is. It is only mentioned that it is a potential box. You see, so as it is not mentioned the kinds of potential box, whether it is symmetric or asymmetric. So what you have to do, you have to assume that this is a infinite potential box of a, or you can say asymmetric box. Okay, infinite asymmetric box. Okay, of length 0 to a. But for asymmetric or symmetric, the the formula of energy is same. Okay, okay. So now what you have to do, we have to find the energy E1 and E2. Then we have to find the relationship, what, how they depends with each other. Okay, so let's see the solution. Okay, so this is the infinite potential box 0 to a. Okay, the length, the dimension is 0 to a. Okay, and this is the formula. Okay, En is equal to n square pi square s square by 2m a square. Okay, so what you have to do, as it is mentioned in the question that it is the energy of lowest state. That means in this type of system, okay, that is infinite potential, well, the n value starts from 1. Okay, so if you put 1, that means the lowest energy state, then you will get a 1 square pi square h square 2 capital M a square. This is, make it equation 1. Okay, this is E1. Okay, now the second case is, now the second case is, now the second case is, now the second case is 0 to a by 2, because in this case the dimension of the potential value has been reduced to a by 2. Okay, from 0 to a by 2. Okay, and the mass has been doubled. Okay, to capital M. Now if you put this condition here, you see this capital M, instead of capital M, replace this 2m. Okay, and in the place of a you have to put a by 2. Okay, so after putting and after neglecting whatever you can neglect, okay, that like 2 can be cancelled with this 4, because a by 2 square. Okay, there is a 4 in the denominator. So after solving, you will get pi square h square by capital M a square. This is equation 2 and equation 1. What you have to do now? So dividing equation 1 and equation 2. Okay, so after solving, you will get 1 by 2. That means E1 is equal to E2 by 2. So option B is the correct one. Okay, so now coming to 74 number question, it is given that in a three-dimensional crystal, the plot between density of state, electron versus energy. Okay, that means we have to draw a graph of density of state, which is a function of energy, versus energy. Okay, okay. So how we can do? How we can do? Let's see. Now you see, first of all, we have to draw a graph, or you can say a diagram, which through which you can find the density of states. Okay, okay. So how can you find the density of state in a region? Let take a region. Here I have taken. Here I have taken. Okay, so here I have taken two regions. One, you can say this is a spherical cell. Okay, the inner radius is k and the outer radius is k plus dk. That means dk is the thickness of that spherical cell. Now what I have to find? We have to find the density of state lying in this region. In this region of a thickness dk. Okay, so how can you find? How can you find this? This is the formula. This is the formula. Gk dk is equal to g, where g is the degeneracy, 4 pi k square dk by 2 pi by l to the power 3. Okay, this 2 pi l is the lattice point distance, the distance between two lattice point. Okay, in reciprocal space. Okay, okay. So as we are considering it in 3 dimension, that means we have to power. Oh, sorry, we have to power. So we have to cube it, because we are dealing in 3 dimension. Okay. So now for electron, E equal to this, E equal to h square k square by 2m. Okay, where this m is the mass of an electron. Okay, now if you differentiate this, that means d to get this dk. Okay, because we have to put this dk here. You see, there is a dk here. We have to put this dk after differentiating this equation. Okay, so you will get in terms of d some expression, because this is in dk. So after putting in terms of e, you will get this ged. Okay, and where this 2 come? Where this 2 come? This 2 is coming from this degeneracy for electron, because the spin of electron is half. So 2s plus 1, that formula will give the multiplicity. That means the degeneracy. Okay, so g is 2 for electron. Okay, that's why this 2 is appearing here. Okay, now after solving this, you just see where this e is present. Okay, this is the, here is a e is present here in the power of 1, and there is a e present. Okay, in the power of minus 1 by 2. So after multiply, you will get 1 by 2. That means in 3D case, this is for 3D. Okay, in 3D case, okay, this is the case. In 3D case, the density of state versus E is looking like how it will look. It will look like this. This is a parabola. Okay, as in the question it is mentioned. Okay, this is a parabola. So option B is the correct one. Okay. Now if you want to know what kind of graph it will give in case of a 1D, 2D like this, then this is the case. In for 2D case, the degeneracy does not depend on energy, but for one dimension it depends on e to the power minus 1 by 2. So the graph will be like this. Okay, now coming to last number of this video, it is given that in case of superconductor we have to find the relation. Okay, how can you find? Now you see, to do this question you should have some background knowledge on superconductivity. What is superconductivity? Actually, any material which show zero resistivity, that is rho zero, at some critical temperature, below some critical temperature. Okay, that kind of a material is known as superconductor. Okay, okay. Uh, Actually, this superconductor are nothing. This is because it appears in below some temperature. Okay, material is same, but below some temperature it behaves like something. It plays, it shows some character. Then it is known as superconductor. Okay, like a T smaller than Tc. You see, I have drawn two diagram here. First of all, this is the material. We don't know what kind of material it is. Okay, and at a T greater than Tc, this Tc is defined for the particular material that you have taken. Okay, because this Tc varies from material to material. So this Tc means this Tc belongs to this material only. This Tc, okay, this Tc belongs to this material only. Let's suppose you exchange this material with, or you can say if you replace this material with some another material, then the Tc will change. Okay, that means uh, to to achieve this superconductivity nature, then you have to decrease the temperature of that material to that Tc, that corresponding Tc that belongs to that material. Okay, for example, I have taken this material whose critical temperature is Tc. Okay, so now when the material's temperature is greater than Tc, okay, then you can see that this external magnetic field that I have applied, okay, it is passing, or you can say penetrating through that material. Let's suppose this is south pole and there is a north pole. These are strong magnet. Okay. If you do this, you can see that the magnetic field lines are passing or penetrating through that material. But when you cool it, okay, you see, I have cooled it below a temperature Tc. I have cooled it below a temperature Tc. This is the case of a T10 less than Tc. Okay. In this case, you see that the magnetic field inside the material is 0. But before, you see, before there is a net magnetic field. In this case, when T greater than Tc, in that case, there is some magnetic field present inside the material. But when T is smaller than Tc, in that case, the magnetic field, net magnetic field inside the material is 0. And you see, now this material is behaving like a diamagnetic substance because it is repelling the magnetic field which are coming towards it. Okay, so it is repelling. That means it is behaving like a diamagnet. Okay, now you see why this magnetic field inside the material becomes 0. You see logically. Okay, that means some magnetic field, some induced magnetic field has been created inside the material, and the external magnetic field both add up to 0. So that's why this net magnetic field inside the material is becoming 0. You see, I have drawn here this downward arrow means this is M. This is the induced magnetic field. Okay, and this upward arrow means the magnetic induction that is penetrating inside that material. Okay, both are adding to give 0 because the intensity of this and the intensity of a external magnetic field and the intensity of a induced magnetic field both are added, and the net magnetic field becomes 0. Okay, that T smaller than Tc. Now we know that M equal to J M. Okay, M equal to J M, and we know that for any material the magnetic field is can be defined as a mu naught h plus m. Okay, now if you put this m equal to j h here in the place of m, then, and we know that for this case b equal to 0. Now you put b equal to 0 here, then after putting, then you will get that j equal to -1. That means what? It is a perfect diamagnet, because for perfect diamagnet we can achieve this case j equal to -1. Okay, so hence we often called superconductor diamagnetic nature. Okay, so hope you got the answer. Thanks for watching.